Hello, my sophomore physics students. How are ya? I hope you're doing great. Like I said yesterday, today is gonna be a day. I hope it's really great for you. I know that remote learning, especially with these long blocks, is challenging. So I appreciate you logging on and, getting into this learning environment. Whoop whoop. Okay, enough of that. Let's just get started. So this is going to be a presentation on the science of nuclear physics, and now I'm gonna just like preface this and say this is challenging stuff, one, to understand, and two, to kind of like, again, understand. So again, if you have any questions, feel free to, reach out to me or even Mr. Shaw. Mr. Shaw knows this stuff inside and out because he used to work in a nuclear power plant, which is insane to think about, that we have a teacher in this school that has direct experience with this stuff. So with that, let's get started. So starting off, let's think back to when we were talking about the atom. And so, as we know, atoms are made up of three subatomic particles: the proton, the neutron, and the electron. And also, as we know, the protons, they have positive charges, neutrons, they have neutral charges, and electrons, they have a negative charge. And remember that the charge that we have assigned to them is a fundamental idea. And so what we know about this fundamental idea is that like charges are going to repel and unlike charges are going to attract. So again, atoms are composed of three major components: positively charged protons in the nucleus, negatively charged electrons orbiting outside of the nucleus, and neutrally charged neutrons inside the nucleus as well. And so remember that the atom is always striving to reach an equilibrium. It's always striving to have an equal number of protons to an equal number of electrons, or no charge. And so typically the number of electrons matches the number of protons. So within the nucleus, we actually have these things called nucleons. And so what a nucleon is a proton and a neutron, and they're actually bound together by an attractive nuclear force. So again, we have this positive charge, we have this neutral charge, and between them, there is this bonding force. And if they are bonded together really strongly, then we call those things a nucleon. And so this force that is bonding them together, we call the nuclear strong force. And so the nuclear force of the attraction is strong only over a very short distance. And so again, go back to our ideas of electric charges, right? As we increase the distance between those charges, well, then the force decreased. Kind of the same idea here with our nuclear strong force, that if we were to separate this proton and a neutron even a little bit, then there's not going to be as strong as a force as there was previously. So again, it depends on the distance between, and it has to be a really short distance. So again, within the nucleus, if protons are not close to one another, again, if those protons aren't bound by that nuclear strong force, then the electrical force of a proton and a proton are going to repel. So again, think back to electrostatics, where like charges, a positive and a positive, are going to repel. So if you increase that distance just a little bit, then they're going to repel each other, again, to that electrical force between them. And so neutrons and protons provide stability between electrical force repelling and the strong force attracting. So there's a kind of balance here where if they get too close, then they're going to be this nuclear strong force between them. If they just get a little bit more separated, then the electrical force is going to take over and it's going to separate them further. And now let's talk about our electrons. And so we typically have seen our electron model within like this planetary model, where we have like our positive nucleus, which is made up of our protons and neutrons, and then these electrons that are orbiting, but we kind of see their orbit. where in reality we don't really know what our electron's internal structure looks like. We just theorize these ideas. So that model can be like the planetary model, which is the typical model that we would see. It can be in a wave type model. So again, our charges sometimes act as particles, sometimes act as waves. And so they can also be in a cloud model. And so we do know that electrons orbit the nucleus on the atom, but we just don't know what their structure looks like. And so we have to pick the best representation for our data. So with our electrons, the planetary model has been replaced in one where electrons are represented as clouds, especially when we're looking at our nuclear reactions. It's best to look at them in an idea instead of like a shell-like model, a shell-like planetary model, I should say, but to now look at them as organized varying levels of a cloud. And so the shading of that cloud is going to represent a stronger nucleus attraction to that atom. I'm so sorry if you can hear the dog. I'm so sorry. But basically, the closer that these electrons are to the nucleus, the stronger that force of attraction, right? And so the stronger that shading is going to be. The further away, the less force of attraction there, and so they're going to be a bit more spread out. And so the shading is going to be not as dark. Okay, so the force is a little bit weaker, so the shading is going to be less. And so the history of the atom and theories and models, there has been a bunch of different theories to which the model best represents. So we typically, again, either look at the nuclear model or the planetary model. And the planetary model is typically what we represent as Niels Bohr model. And that's typically what we see in class because it's a bit easier to recognize when like our electrons are further away from the nucleus and how they can be easily dislodged from the nucleus, from the atom itself. But then the nuclear model is also beneficial because we can visually represent those orbits of the electrons itself. But Schrodinger's quantum model with the clouds is really helpful when you're getting into quantum mechanics and into that quantum realm. So to kind of like based off of like predictability. So let's look at radioactive decay. So when you have a radioactive element such as uranium, this element can actually decay. And so it can actually decay into 3 different types of radiation. And so what this radiation really is like an energy. And so it can decay into alpha particles, it can decay into beta particles, and into gamma rays. And so if you remember back a couple of cycles ago when we were talking about the electromagnetic spectrum, your gamma rays are going to be the highest frequency wave on our electromagnetic spectrum. Okay. And so when we have this radioactive element like uranium, it's going to break apart. It's going to decay into these things. It's going to decay into an alpha particle, beta particle, or gamma ray. And so some elements will naturally decay while others do not. Okay, so our alpha decay, an alpha particle is made up of 2 protons and 2 neutrons. Kind of think of like a helium atom, right? So there's an equal number of your protons to your neutrons. And so what this alpha decay really is, if you can visualize this within your atom, you know that a proton and neutron, they have a really large mass. And so what that means is they're really hard to move due to their inertia, right? They have a lot more inertia than something we would typically see moving like an electron. And so when this alpha particle decays, it can't travel as far as, let's say, a beta particle or a gamma ray, and that has to do with its inertia, that heavy mass. A beta decay is simply an electron. All right, so ejected from the nucleus where a neutron is transformed into a proton. Again, it's kind of really difficult to understand, but ejected from the nucleus itself is these electrons that are being basically, getting rid of it in the atom. And so what a beta decay is, again, think of the mass of your electron. Your electron is really, really small, right? It's smaller masses than even your proton and neutron. And so what that means is that they can travel a bit further than your alpha particle, but they're still not as hazardous. We'll get into hazards in just a second, but let's talk about our gamma ray. So again, as we know, it's the highest frequency in energy of our electromagnetic waves. So again, think back to that cycle when we were talking about radio waves and X-rays and visible light, and when we were talking about infrared and ultraviolet, and we were also talking about these gamma rays. I'm so sorry, let me pause real quick. Okay, getting back to gamma rays. So the gamma ray is the highest frequency energy of our electromagnetic waves. So again, what that high frequency means is really short wavelengths. So what this means is that your gamma rays can travel. So radiation is honestly made in anything. So like in medicine, in food, in coal, nuclear power plants, and weapons, in consumer products like TVs, monitors, computers, smoke detectors, and then we can also find it in cosmic rays, earth, minerals, randomly in air. And so what this pie chart represents is it's a show of origins of radiation exposed for an average individual in the United States. So honestly, we get exposed to radiation almost every day by pretty much all of these things. And so when we are looking at how dangerous our alpha, our beta, and our gamma rays are, it's really important to look at their makeup, right? So alpha, again, is 2 protons and 2 neutrons. And so, like I said, their mass, they have a lot of mass compared to other things within your atom. And so what that means is they don't travel very far. So we can actually protect ourselves from alpha particles if we were to just like throw up a piece of paper in front of it, or cloth, or some type of suit. Okay, that alpha particle isn't going to travel as far. It's only going to travel a few centimeters in air. Where it does get dangerous, though, is if it was to be ingested somehow, if you were to breathe it in, if you were to consume it. It typically doesn't penetrate your skin, but again, it is dangerous if you ingest it or inhale it. And so one of those things that can be caused is like lung cancer and stomach cancer. So beta particles, again, just think of your electron. That electron has a smaller inertia, which means that it has less resistance to change its motion. And so it can travel pretty far. It can travel a few meters. And so it can cause, some skin burns if you were to be overly exposed to your beta particles. And it's particularly dangerous, again, if you were to ingest it or inhale it. But it can be stopped with like aluminum foil or a better like hazmat type suit. And it can also, like I said, cause these radiation burns if it's overly exposed, if you were exposed over the recommended amount, which is you don't really want to be exposed at all to it. But so what this really means is that this is just kind of like the general health effects that could be caused by your alpha and beta particles, and again, it kind of depends on your exposure to it. The more that you get exposed to these things, the more dangerous that they do become. So now let's talk about gamma rays. And again, it's that high energy wave, high energy, high frequency. And so these things can travel extremely far. So just from our diagram, like it goes through and travels through the paper, it can travel through your entire body, and then through some wood, and then through concrete, and probably then through lead. These are really, really powerful rays. And so they don't lose their energy very easily. So their half-life is basically like every 500 feet. And so they can penetrate your entire body and mess with your DNA and give you burns, all this other stuff. And so lead is a good protection, but again, it's stuff that you don't want to be around. And so neutron, is a high-speed neutron, and so it can travel through thousands of meters. Concrete or water can effectively stop it, but only radiation that can cause other materials to become radioactive, I should say. So when this neutron comes into contact with other things, it can cause that thing to become itself radioactive. And so a guide to different types of radiation, like our alpha and beta and gamma rays. So again, feel free to kind of look at this. And when we get into our work, so from this, we can see, that the alpha particle, that's going to be stopped by paper. The beta particle, that's going to be stopped by aluminum. And gamma, it's can only be stopped by lead, honestly. So they are really, really bad. So let's keep going. And let's talk about nuclear reactions. All right, so what we're going to talk about is nuclear fission and nuclear fusion. And so fission is the splitting of atoms, and fusion is the combining of atoms. So they're being fused together. So fission is typically what you would see in like a nuclear power plant, where fusion, you can see a great example if you look up at the like morning sun, right? So fission is the split of atoms apart caused by an unstable nucleus, and so the electric force actually overcomes the atomic strong force. So again, think back to what the atomic strong force is. It's like that force between that proton and neutron. And so when they are separated by a further distance, then that electric force is actually going to take over. And so typically with a larger nucleus like uranium, like that radioactive material, fusion is the combination or the combining of those atoms together. So the atomic strong force overcomes the electric repulsive force, and it's typically with a smaller nucleus. So fission is a nuclear deformation leads to fission. It's repelling electrical forces dominate attracting nuclear forces. So the nuclear force is dominant, and then there's a critical deformation that happens, and then the electrical forces is dominant, and so it actually splits them apart. And so with fission, it's a typical reaction starts with one neutron, and then it slams into another nucleus, and that nucleus becomes unstable, and then it just keeps on this chain reaction all the way through. So more neutrons are produced when the uranium fission, and so it releases about 7 million times the energy as one TNT atom. And so again, it's all about this chain reaction that occurs. So a chain reaction is a self-sustaining reaction. And so an initial event causes additional reactions within the process. And so it keeps going on and on and on. And this is also a danger of fission, is that it's hard to stop this chain reaction that keeps occurring. This continuing breaking of this atom, and then having that break, combine with others, and then break those, and then combine with others and break those, as you can see from this diagram. And so chain reactions, why don't chain reactions occur naturally? And again, it has to do with the size of the nucleus that is needed. And so it's a really rare isotope, U-235, which is a type of uranium. And so it's only about 0.7% of uranium. And the majority is U-238, which is a stable version of uranium that can absorb these neutrons. And so the critical mass, so what a critical mass is the amount of mass of an unstable atom needs to sustain a reaction. And so in order for this chain reaction to keep occurring, there has to be a certain mass involved. And if that mass isn't met, then it's either going to be subcritical or supercritical. So subcritical mass is one in which the chain reaction actually dies out because there's not enough mass. And then a supercritical mass is one which the chain reaction actually builds and actually becomes more explosive. And so what you can actually do to kind of get this idea of like, well, why is mass important, is to think of E equals mc squared, right? One of the most famous physics equations. And so what this does is it relates mass and energy as essentially the same thing. So mass is like a super strong battery, right? And so if you have more mass, that means like you have more strength to your battery, so more energy. And so it stores energy that can be released. And if when the mass decreases, then that energy is also going to decrease. So when mass is lost in a reaction, it is converted into this energy. So energy released is equal to the mass difference times the speed of light squared, or E is equal to mc squared. And this is known as the energy mass equivalence. And so if we're looking at the graph, we can actually tell a lot of things from it. So the higher the atomic number, the greater the mass per nucleon. And that makes sense because the higher atomic number, the higher protons, so the higher chance that a proton and neutron are going to be bound together by this nuclear strong force, and so the higher energy level. And so the lower atomic number after iron, the higher mass per electron. So the lower atomic number, the higher the mass per electron, so the higher energy level. So you'll also notice the lower atomic elements have a much higher mass, and so releasing energy using these elements produces more energy. So again, this is just from the energy mass equivalence, that if we were to release this energy using the elements that have lower atomic elements that have much higher masses, releasing this energy would cause a more energy to occur, right? And that's known as fusion. Okay, so when we're looking at fusion, again, it's with these smaller mass types, it's with these smaller atoms. So a proton has more mass by itself. Then inside a helium nucleus, you can see that that energy is going to increase. So mass of a single proton is more than the mass per nucleon in a helium-4 nucleus. So therefore, if combined, it can release extraordinary amounts of energy. And that energy is called this fusion nuclear reaction. So atomic nuclei are positively charged. And so for this fusion of these two atomic nuclei to occur, there have to be occurring at really high speeds and really high temperatures. So it must collide at very high speeds to overcome the electrical repulsion. So again, think back to electrostatics. These are both positively charged nuclei. So they automatically want to repel from one another. But if we were to force them into this reaction, then we would need to collide them at very high speeds. And so high temperatures combined with other factors can cause these high speeds. And so what is created is helium, energy, and a neutron. So a good example of nuclear fusion is high temperature starts this reaction, but a good example is the sun. So again, this high temperature is really important to having these really high speeds. And so the high temperature is actually necessary in order for this chain reaction to keep occurring. If those temperatures decrease, then the speed's going to decrease, and then that, reaction will stop. So a good example, central part of the sun. So 657 million tons of hydrogen converted into 653 million tons of helium each second. So it's missing 4 million tons of mass discharge as energy, which is crazy. So the sun is not burning, it's just emitting all of this energy. So with our nuclear power plant design, and again, you'll learn a little bit more about this within our classwork itself, but this is an example of a pressurized water reactor. And so it uses 3% enriched uranium, which is like 3% of U-235. And nuclear weapons actually use about 80% or more. So it doesn't use up a lot of uranium, but it's really powerful in the fact that it can use these tubes. So it can use these tubes full of that radioactive material, and then with this combining, this breaking apart of the nucleus, that energy is released and it actually heats up this water. That water turns to steam. That steam is used to turn a turbine or a turbine, and that turbine is using mechanical energy, and that's getting converted into electrical energy within a generator that we can actually use. And then that condensing water is actually sent to a cooling tower. So when you typically think of like nuclear reaction power plants, you probably think of this little thing right here, especially if you've ever watched The Simpsons, right? And so it's actually just a cooling tower. So basically it's converting the steam back into a liquid, all right? Or it's cooling down that water, okay? Through that condensing water, then back up, that's sending the steam out, and then all that good stuff. So let's keep going. I think there's one more. Nope, that's it. All right, so start working on your classwork if you have not already.